But we're doing policy gradient estimation, and just a quick recap. So the first method we saw basically took a policy that's parameterized by some number of parameters. It tweaked each parameter. Like here it's tweaking theta 1 plus epsilon. It would run many trajectories of the policy, see how well it did. Did it do better or worse? And then it would move that parameter in the direction that makes it do better, depending on what those runs did. And the problem with this was you have to do a whole bunch of trials. In particular, you have to do these n trials for each of the parameters. So that's prohibitive if you have a lot of parameters, which if you're dealing with neural networks, you will have a lot of parameters, millions sometimes. So we don't want to do that. We wanted a method that we could just take our current policy, run it a number of times, 10, 100, who knows, and then estimate the gradient of that policy just from those runs. Then take a step in the gradient direction and do the thing again. Okay? So we wanted something that does not scale in terms of the number of trials with the number of parameters. And for that, we introduced this idea, which is captured by the policy gradient algorithm, policy gradient theorem, we should say. And this is going to be used as the basis for most policy gradient algorithms. So it's good to understand this. And we started to piece together intuition for this last time. If you remember, there's basically a few things you want to pay attention to here. So this is an expectation symbol, right? So this is the true gradient. So remember, rho was the value function of the policy with the parameters theta. If you start in the initial state, so we're assuming in a fixed initial state without loss of generality, but we want rho to be large. And so the exact gradient is given by this expression. And we have this expectation, and the random variables in the expectation were S and A. So this corresponds to a state and an action. And they're distributed according to the policy here. So, and in particular, if you run the policy many times, there's some distribution over states that it ends up in, and there's some distribution over actions taken in those states. And the SA pairs are distributed in this expectation according to those runs of the policy. Okay, so that's where the randomness is coming from in this expression. And inside we had two things. One was what we call the score function, which basically is a vector that points in the direction to the direction in parameter space to increase the probability of taking action A in state S. Right? Then we said this is sort of weighting that direction by sort of the Q value of taking A in S. And so you can say these gradient directions are sort of weighted by how good they are, how good the actions will be if you were to take them. And so it's very, very much has a policy improvement feel, right? Because we know if you were doing real policy iteration, right, exact policy iteration, you would have, like if pi theta was your policy, you compute the Q function, and the improved policy is just the maximum action of that Q function. And so this is just saying, well, we can't exactly do that, but we're going to take a step in the parameter space that will tend to give us better Q values, right? And if this is a positive value, you're going to move in a good direction. All right, so I think that was pretty much all of the intuition we talked about. So are there any questions about this policy gradient theorem before we move on? Right, it's pretty important that you understand the pieces of it, because that's sort of the you don't want it to just be something you memorize. It's actually a pretty intuitive form at the end of the day, and the proof in the book is relatively short. You can actually go through that. So we're going to use this now to actually design some algorithms. And what part of this expression do we know exactly, and what parts do we not know exactly? Right? Because they're telling us what the gradient is equal to here, right? So they're saying it's equal to this. Why don't we just compute it? Just write down the closed forms for Q and this, and write down the closed form for the expectation, and just compute it. So what parts of this are difficult? Do we not necessarily know, or what parts do we know? Yeah. Okay. So you're talking about this one here. Do we know that exactly? No. So we have our hands on the policy, right? We know pi theta. Right? That's something that we define. We've got it. We can do anything we want with it. But nobody gives us Q pi theta for free, right? Because pi theta basically you can run it, but it doesn't tell you how good it is to take action A and then run it, right? That requires one step look ahead. You're not going to have a nice closed form expression for that unless you try to compute that or estimate it yourself. How about this term here, the score function? Can we get our hands on that exactly? What do you think? This is the gradient of the log of the policy applied to a state and an action. What do you think? Yes. Yeah, so why is that? Why can we do this exactly? This score function part.
It's just a parameterized function, and it can be taken derivative also.
Yeah. So we pick the form of pi theta, and we're if it's a neural network or some other functional form, you're generally going to make it a nice form that you can work with, and then taking the log of that. That's log isn't anything crazy to work with, and then that's generally going to be differentiable, or it will at least have a subgradient, and then you can commute the gradient. And most the modern deep learning libraries that are available will just do this for you automatically. Right? They do auto differentiation. You just define the functions and they'll differentiate. So we can do this exactly. So this is exact. This is not exact. We have to figure out how to approximate this. Then the expectation itself, right? That's another animal too, right? So it's going to be hard for us to get the exact probabilities of all the states and actions, state action pairs under the policy. Right? Get a closed form for that. So that's the other thing that we don't have exactly. But that's not going to be our major problem. So that leads into the question. So I should say, up till this slide, this is where sort of the quiz is going to go up to. Right? That's where we were on Friday, and so all the reinforcement learning material we've talked about until this slide for the quiz on Friday. And the quiz on Friday is in a different room because they have the IAB, the Industrial Advisory Board meeting in this building. It's going to be crazy. They're probably going to be using this room. So we're going to be in MLM 019. So I sent a course reminder there, and I'll send another reminder on Thursday. So you don't forget, because it's unfortunate that's a quiz day. It would be too bad to forget that. All right, so we're leading into this question. So we expressed it as an expectation, and this is something you want to actually, really, have good intuition about. What often you see people trying to express things as expectations, and why do they do that? Why is it useful to express the gradient as an expectation? Like usually you would think this is a pretty hard thing to compute, right? An expectation over like the state action distribution, that a policy generates. You can't get that in closed form. So why is an expectation useful to derive? No?
We can just estimate it by samples.
Right. So any expectation that you have, right? So any expectation, if you have an expectation here over the variable x, right? So x is distributed somehow, and we have some function of x, right? As long as you can draw samples, xi from x, you can estimate this by just the sum of I, with n samples, f of xi, right? And we already we talked about when we went over the Chernoff bound that this average. So we're approximating the expectation with an average. That average converges very quickly to the expectation, right? So the reason why a lot of times you'll see people try to express complicated expressions that you may not have a closed form for as an expectation is because of this fact. Averages can estimate expectations fairly well. Now, you have to be able to sample, right? You have to be able to sample x over there, whatever the expectation is over. And so can we do that here? How do we sample the state action pairs that are distributed according to policy pi theta? How can we do that? You just run it, right? So that's pretty nice. We have to have a way of running the policy, and that could be in the real world or a simulator. But yeah, our sampling routine's simple. We just run the policy. That's how the random variables are defined. The state action distribution that you get when you run the policy. So that's really, really easy for us. So we know that we can get those samples. So you basically run the policy a bunch of times. You collect your state action pairs, and then you're going to average this over the state action pairs you get. All right. That's now alternatively, another thing that you'll do sometimes is you'll say, okay, I've got an expectation. I'm going to run stochastic gradient descent. Right. So a way to get an exact estimate, an estimate of the exact gradient, you could sample many of these and then average and then do a gradient update. Stochastic gradient descent will just sample one state action pair and then do an update on that and then keep on doing that over and over. So each update is based on, you might say, a more noisy estimate of the gradient, but you can do many more updates to the parameters compared to if you average n things and then do an update. And so often, usually there's sort of a middle ground, right? Doing pure stochastic gradient descent has more variance. Doing the sample n and average has less variance, but it takes more time. And usually in the middle there's a sweet spot. This is the idea behind mini batches. If you've taken neural networks, and the mini batch size is often a parameter that you have to play with. All right. So any questions about this? So we're getting close to being able to define algorithms, right? If we have stochastic gradient descent, at our disposal, we know how to sample a state action pair. Right? We'll just run the policy, and we get a whole bunch of state action pairs. And we know how to compute this. We don't know how to compute this. We don't have our hands on this. So the different algorithms are generally going to be different ways of estimating this, right? If you ignore the formula model that you have, which is kind of a detail of the application. So estimating Q is what we're going to look at now, different ways of doing that. And each way has a name of an algorithm. And today, in this class, we're going to go over some of the fundamental algorithms. And what you see in the literature nowadays is lots of they're usually going to be based on one of these things that we talk about in class, and then they add some tricks, various types of tricks. And you just have to read the papers to look at their tricks. And some of these are interesting tricks. Some are just, engineering type tricks. And we'll talk about a few of those as we go. So reinforce this is actually a fairly old algorithm that came out in the early 90s. Actually, before this form of the policy gradient algorithm theorem was sort of stated, it was sort of derived from the ground up. But we're going to show how this sort of falls out of the policy gradient theorem. So basically, it uses stochastic gradient descent on unbiased estimates using of Q using Monte Carlo estimation. Right. So this is going to be fairly straightforward. So we can get a sample of S and A, right? Samples of S and A by running the policy. So this is how we're going to index it. So notice here we use capital letters because these are random variables. These are lowercase letters because they're specific values that we get when we run the policy. Now, at any point here, we can get an estimate of the Q function, right, by just summing up the reward, right? So if we look at what's an estimate of the Q function of S1 here, right, for A1. So the Q function of S1, when you take A1, well, that's just the sum of the rewards here, after that, because we took A1 and then we followed the policy thereafter. And that's how the Q function is defined. And if you did that many, many times, you took A1 and S1 and then followed the policy and you averaged, it would give you the actual Q function. Here we have just one sample. It's going to be a noisy estimate. But it's an unbiased estimate, meaning that the expectation of this estimate is the true value. We can compute this analytically, as we talked about, and now we can basically get an algorithm. Really simple, right? These algorithms are just a couple of lines long, and you can implement them. Well, if you have all the environments set up so that you can get the information you want from the environment, it's really a very short program using modern tools. So basically, we're just going to loop. And every time through the loop, we're going to generate a trajectory using the current policy. Then we're going to walk along that trajectory and do an update, a stochastic gradient descent update for every time step, basically. And so time step 0, we're going to estimate the Q function for S0, A0 by this sum. And then we're going to do a gradient adjustment. And we move to the next time step, do a gradient adjustment. And that's all there is to it. So you sample a trajectory, and then all the way along, you're going to do one gradient update for every state action pair that we experienced. So this is an algorithm called reinforce. So any questions about this?
So if like certain state action pair, there's two times in one episode, we just count the first one?
Here you'll just count them. Yeah. So you'll just use them all as they come.
So
and
how many pairs we just like counted all the rewards after that?
yeah, so you'll every pair that you see, you'll do an update, and so there might be repeats. And the reason that's fine here, you actually want there will be repeats if there's a high probability, for example, of a state action pair occurring in one, and then you want that to be reflected in the estimate. So any other questions? All right, so the actual reinforce algorithm, this is what the book calls a reinforce algorithm. The original one would sample n trajectories and do sort of averages over those to get a gradient, but this is the stochastic gradient descent variant. So really easy to implement, right? This is extremely easy. And the only hard part in the old days is if this was a giant neural network or something, you'd have to write the code to do that. But if it was a linear function, it was that was really simple as well. So I think so there's we can interpret what this gradient is saying. This is just kind of paraphrasing what we've already talked about, but it's always nice to look at this. So these are the concrete parameters of our policy. And this is an estimate of the cumulative reward of taking action AT in ST, right? So it's after you take that action in that state. If there's a lot of reward, you're like, oh yeah, I'd like to take that action in that state again sometime, right? If you get a big negative reward, you'd be like, oh no, I don't think I want to do that again. And so that's sort of telling you how good your estimate is of taking that action in that state. And then this, as we've already talked about, is telling you which direction to increase the probability of taking that action in that state. And so if you fall off a cliff, this is going to be highly negative, we hope, and you'll move in the opposite direction so you won't fall off the cliff next time. All right? These are all very, very interpretable algorithms at the end of the day. All right. Okay, so let's reinforce. So here's how you would implement it in a modern deep learning framework. You're not going to have to do this explicitly yourself. What you'll do is you'll define a loss function at each step, minus gt log of this, and then you'll run your optimizer a step on trying to. So the reason there's a negative here is we're doing gradient ascent. Usually the optimizers are trying to minimize loss, so we have to have the negative. Here we want to increase the reward, so we're doing gradient ascent. Then you just call your optimizer each iteration and do that. So no gradients, it'll just do it automatically for you. Right? You can have a giant neural network. You just go to town defining whatever network you like. All right. So, and there's tons of code out there for a lot of these algorithms. If you do a search, you'll find some as well, and they'll all have their own tricks. All right. So this is sort of the vanilla policy gradient algorithm. Like if you said what's the most pure policy gradient algorithm, this might be it, right? It's a stochastic gradient descent with an unbiased gradient estimate from Monte Carlo. The issue with it in practice is it will often have a very high variance. So even though everything it's unbiased, which means if you have enough samples, it will converge to the right thing, but the variance can be very large, which means from run to run, your results are going to be pretty noisy, and it will take a long time to converge for that reason. So you want to think of high variance as there's going to be a lot of noise in this learning system, and it makes it harder to pick out the real signal and eventually get to the right place. So a lot of what's done in one of the big things in policy gradient algorithms that you look at, one dimension of improvement is to reduce variance. Try to make the gradient estimates a little more stable. And often you're going to give up, you're going to make the estimates biased a little bit, but that's usually worth it. Often in stats, there's a trade-off between bias and variance, and we'll see where that bias comes in here later on. All right, the biggest idea that people use is something called a baseline, and we'll talk about that in a moment. But what's the purpose of the baseline? If we look at these, this estimate here of the reward of taking action A in state S, part of the variance in that estimate is based on how good the state is. And then how good is the action in that state, right? So there can be, let's say there's just different rooms, and in the rooms you can do different. You have the same action set in all the rooms, but in one room, if you happen to be there, all the rewards are sort of a little less. In this other room, all the rewards are a little more. But there's still, if you're in this room with a little less reward, you still want to act optimally. Right? You still want to take the right actions and maximize your reward there. Here, you still want to act optimally, and you'll get a higher maximum reward. But these gradient estimates don't distinguish between sort of the relative value of a room. Right? So one room, just you inherently get more reward there. The other room, you get less reward here. In the other room, you get more reward. And really what we care about when we're updating the policy is how good is the action relative to other actions, like in this room? And how good is the actions in this other room relative to actions in that room, right? As opposed to comparing actions from the two rooms. That can be confusing because you might be doing the optimal thing in this low reward room and the optimal thing in this high reward room, but this optimal thing in the low reward room won't look so good, right, compared to the high reward room. So you kind of want to get rid of the sort of, I would say, baseline value of these rooms. And you want to update based on sort of the relative value of actions in a particular state or room. Okay? So does that make sense, that analogy? Any questions about that? Another way to think about this is imagine that, so this is a situation of repeated states. Imagine that you run a trajectory and it's a finite length and you have a state repeated in it, right? And let's say one state is repeated in it at the very last step, right? And that state is also in the first step. Now, the reward estimate, the Q-value estimate we get for that first step is going to be quite large, perhaps, because there was a lot of reward after that in the trajectory. For that second occurrence that happened at the very end, there's a very little reward after it, right? And so here you've got two states, and maybe you took the same action in a trajectory, and there's very different reward estimates each time. But it's because it's not anything fundamental. It's just the trajectory ended. And so you'd like to know what's the relative value of this action at the end, based on what you could have possibly got. And so that's just another way that this can materialize. That can actually have a pretty big impact if you don't pay attention to it. All right, so question.
Is the variance of this algorithm being large the same as you saying that the last state will have smaller reward compared to the previous one?
The variance being large is, you could think of it that way. Yeah, so you get the same sort of data, and in one case, you're going to have a big estimate and a small estimate, and that's variance. Because this state happened to occur multiple times at different places, possibly at random. And if we can reduce the effect of the position in the episode, right? Just there's like a fundamental sort of value of taking an action in a state that's unrelated to where it appears in the episode. And so if we can remove that, we'll remove some of the variance, right? And the other variance is, there's always some inherent variance due to just randomness in the domain. But this is a type of variance that we can try to deal with.
Yeah, because if you just update it for t equals to 0 rather than updating for all the states, like wouldn't the variance be reduced?
So you could remove some of your data, right? So we're talking about, so you're trying to say we're going to not use repeated states, right? So t equals 0 will not necessarily cover all the states that you experience.
Yeah.
So that would be a problem. You need to update based on the entire state action distribution. Right. So if we go back to the policy gradient theorem, this gradient is, you have to sort of average over all state action pairs that can be generated by the policy, and you weight by the probability that they can be generated. Right. So you can't just update based on the first one. All right, so good questions. Any other questions about this? All right. And this thing I just talked about, this is something you'll, if you ever implement one of these, you'll sometimes see this if you use the right domain, and it's pretty obvious when you see it. To be like, why is the function approximator so bad? And then you'll look at the data, and there's like two identical data points, and one has a value of 100 and one has a value of 1. You're like, oh yeah, that's probably a hard thing to estimate. All right, so now what we'd like to do is reduce the variance. And we can do that by subtracting something we're going to call a baseline from this Q function, right? And so the Q function has sort of information about how good the state is and how good the action is. And we're going to try to have a baseline that sort of removes the stuff that's just about how good the state is, right? So this is going to be called a baseline function. You'll see this term all over the place. Almost every policy gradient algorithm that's used in practice now will use a baseline function. So the baseline function can be any function at all that only depends on the state, right? So you can certainly add a baseline function that's a bad one that will make you do worse, but we're going to try to add ones that make us do better. So this is the policy gradient theorem with a baseline. And notice you still have an equality here. So this is kind of a surprising thing at first, that you can just subtract some arbitrary function, right, of S. So it's critical that it only depends on S. So you can subtract some arbitrary function from this Q value and put it inside the expectation, and it still has equality here. Right? So this top original policy gradient theorem is just a special case of this bottom one where the baseline is 0. Right? So we're gonna show why this is true, and it's actually a reasonably easy thing to see once you work it out. But at first it seems kind of crazy that it can just be any function and still you have the expectation giving you equality to the gradient. So we're first going to see why this is true, and then we'll talk about baselines that you'll use. Okay? So why is it true? Well, we can first sort of write this out. So this is just writing out what we had on the previous slide. Now we're just going to break it into two parts, right? The expectation is a linear operator, so we can break it up like this. And this is the original policy gradient theorem, right? That's what this is from. And this term here, the expected value of the baseline multiplied by this score function, turns out to be equal to 0. And we'll see that on the next slide. So this slide is why it's correct. Basically, the expectation of any function of S multiplied by the score function is going to be 0. So let's see why that is. And so the baseline won't impact the expectation. Oh, and yeah, so we should say, that while it doesn't impact the expectation, it does impact the variance. Right? So, and in particular, when this sort of idea first came around, people would try to figure out what is the minimum variance baseline. Right? And of course, that's something that you can't really get your hands on, so you try to estimate that. Right? So what is the minimum variance baseline? And because any baseline is unbiased, you just find the minimum variance one. All right, so what we want to do now is show, well, why is this expectation in red 0? And that's a very short little derivation here. Requires a little bit of a pretty common notation. So we're going to define this to be the distribution of states under pi theta, right? So mu in the subscript pi theta, that's the distribution of states. You run pi theta many times. What's the distribution of states that you see? And so you can rewrite this expression as follows. So we're now going to sort of weight everything. We're going to sum over states, weighting them by the frequency that they occur. This is something you can write this out with a little bit of work. It's a fairly annoying thing to derive, but you can do it because there's a lot of the notation's messy. You have to do a lot of nesting and keeping track of things. But this is a very common thing to see. So you first break it up by the frequency over states, and then you break it up by the frequency over actions. Because the distribution over actions, if you know the state, that distribution is fixed by the policy. Right? So this is equivalent to this original expectation. And then all we do is we do a common trick. We actually, this is just in calculus, this is the log, the derivative of the log with the chain rule applied, right? So derivative of log of x is 1 over x. So that's a chain rule, nothing fancy there. And what's nice is, well, this cancels out, right? The policy cancels out, and you're left with just this. B of S does not depend on the action, so you can move it out. So that's why it's critical to have B of S not depend on the action. And then this term here looks a little strange until you rewrite it. Then you just take so we're in a setting where everything's nice and you can move the gradient outside of the sum here. And if we were dealing with continuous factors, this would be an integral, and generally people assume everything's nice, so you can do that. And then, well, what's the value of this? The sum over A of pi 1, right? So there you go. And the gradient of 1 is 0. So it falls out. I mean, this is just basic calculus and algebra. So there you have it. This is our new policy gradient theorem with a baseline. And so now we can set this baseline to anything we want. And in particular, we want to set it to something that we think would decrease the variance. And based on what I talked to you about earlier, this Q function sort of has boiled into it, the value of the state, and then sort of the value of the action in that state. What would you take to be a baseline? Like if I had to ask you, and you don't even have to be able to compute it, but what would you want to use as a baseline if you had to choose some function? The value of the state, and under what policy? Well, if you have it, so I'm letting you use that. That may not be the best here, in the sense that you may be starting off with something that's very far away from the optimal policy, and this Q function is based on whatever policy you have right now, and so you kind of want to remove the component of the state value that is sort of based on our current policy. Yeah. Any other ideas for a baseline? So it is a value function. That's usually what people will use. But the value function of what?
The expectation under the current policy.
So yeah, the value function of the current policy at S. Yep. So that's there aren't too many other answers you could give. So we got pi theta here, and the optimal policy. I don't know what else we would say, but that's the typical choice. The value function of pi theta, right? Because think about what we're doing here. And when you do this, when you have the baseline, this is something in the literature that's called the advantage function. Right? You'll see this talked about all over the place. Any policy gradient algorithm paper you pick up nowadays, they'll work with advantage functions, sometimes without even defining it, even though you probably should define it. But the advantage function of a policy for a state-action pair is just, well, how much better is it to take A and S follow, and then follow pi than just following pi from S. Right? So the policy pi theta may not take action A in state S, or the distribution will not put all the probability to A, and so these will not necessarily be equal. Now, if you're doing a policy iteration, right, you would just pick out the maximum A here, and you would that's how you would update your policy. This is we can't do policy iteration exactly, and so but whenever in policy iteration, if you were to pick an action that gives you a positive advantage for every state and update the I think you had a written assignment, a written problem about this, where you could modify policy iteration so that you don't have to pick the maximizing action, but just some action that improves on the current value. And that version of policy iteration works. Basically, that's saying you pick an action that makes this positive. And if you always can do that, you're going to have an improved policy. So this is, it makes a lot of sense, right? This is now, if we have these two rooms, one that's like, small values generally and large values generally, this value is going to be small in the small room and large in the large room, and it's going to kind of negate this the effect of the room, right, or the state in this case. So any questions about the advantage function? Right. So very important to know what this is. As I said, pretty much every policy gradient algorithm will work with advantages nowadays. But the challenge is we don't actually know, just like nobody gave us Q, nobody's going to be giving us V as well, right? That's not something you can get for free. So maybe it's a little easier than getting Q, because Q has to be defined for all actions, but still, you're not going to have somebody hand that to you like they hand you the policy parameterization. So this is policy gradient theorem, and we can modify reinforce so it uses a baseline. And this is something that was done way back in the early 90s, and we still have our Q estimate based on that. And now we're actually going to use value function approximation to try to estimate the value function of the policy. And you remember back when we were learning about policy evaluation, we were like, is it really that interesting to evaluate a policy? Right? We all want to be optimizing policies. We started off with policy evaluation. And I said, well, one reason is that the optimization algorithms are basically just evaluating an explore-exploit policy. The other reason is some of these reinforcement learning algorithms that you're going to learn about later use policy evaluation as sort of an inner loop type thing. And here is really one of the major use cases. You're going to use policy evaluation methods to estimate this baseline of the current policy. And so let's see what that looks like. So we're gonna pick some policy evaluation architecture. So we function approximation architecture. So we started off, when we did that, we talked about linear function approximation, and we said, you could do this with a neural network as well. And so that architecture is going to be V hat WS, where W is the parameters of the value function approximation. Okay, so it could be a neural network. Usually that's what it is nowadays. W is a parameter. Okay, so we already talked about that. And we're going to learn this for this particular algorithm using Monte Carlo. And we're going to do that in parallel with policy learning. So none of this stuff is going to be sound at the end of the day. We'll talk about that in a moment, but it will tend to improve things for you. So this is very similar to the previous code that we looked at. So we run an episode of the current policy, and then for every step, we're going to do a stochastic gradient descent update. And just like before, we're going to compute this return to go, the reward to go after the time step we're at. And the advantage is just going to be estimated as the reward to go, which was our Q function estimate, minus this value function estimate, the approximate value function estimate at S of t. Okay? So this is going to try to, if your value function estimator is doing well, it will say, oh, in this room over here, the slow reward room, is generally smaller value than in this high reward room. Right? Even though it might not be exact, at least you might get some qualitative differences out of your value function approximator. And after you define the advantage, we're going to do an update to both the value function estimator and the policy parameters. And it's interesting, they both have a very similar form. So if you think about this, what is this? This is the reward to go from time t. And that could be used as a value function estimate in itself, like a Monte Carlo value function estimate, right? You ran the policy. And this is our current estimate, right? So this is sort of the error in our value function estimate, this advantage. So you can interpret it as an error in your value function estimate in this context. And so this update here is, if you go back in the notes, you'll see this is the error in our current estimate times the gradient, right? That's how we adjust the parameters. And then we just adjust them in that direction. And this is just the reinforce update that we saw before, but with the advantage function instead of the just g. Previously, we just had g here. And notice that we have two different learning rates. Generally, what you're going to do is you're going to have two different optimizers, right? One for the value, you'll initialize an optimizer for the value function approximator. You'll initialize one for the policy, and you'll just keep you'll call those separately. Usually, if you're using a modern library, you're not going to sort of change the learning rates by yourself as things go on. Whatever your optimizer is will deal with that. You might specify some parameters for the optimizer, but these definitely are going to want to be separate because you're dealing with very different types of functions that you're optimizing. All right. So any questions about this? All right. This is almost getting to something that is pretty usable. You could actually do this and use it and have reasonable luck for a lot of problems. All right. And it will work for any crazy neural networks you want to use for pi or v. You can use them. Or anything else that's differentiable. Yes?
So how do we estimate the W just by some neural network? Another neural network?
Yep, it would be another neural network. And I'll show you some examples. We're going to talk about a particular algorithm called A3C. Often they have a neural network that has some layers from the input, and then it will have some shared representation that is used for both the value function learning and the policy learning. So we'll see that later. But it's just arbitrary neural network. Could be linear, could be 1,000 layers deep if you wanted to. All right. So any other questions? All right. So looks like we're about out of time. So next time we're going to move beyond the reinforce algorithm and show how you can add another layer of function approximation to further improve things here. All right.